Linear Regression, An Introduction by J.C. Long, Andrew Skipsack, and Matthew Keefe. The concept of linear regression was discovered in 1875 by Sir Francis Galton, cousin of Charles Darwin, while studying heritability in pea seeds. He distributed seed packets with different variations of seeds with uniform weight to several friends who grew the pea seeds. They returned the daughter seeds to him, which he then laid. When he compared the weights of the daughter seeds to the mother seeds, he found that the median weights of the daughter seeds from a particular size of mother seeds approximately described a straight line with positive slope less than 1.0. From this, he identified that the slope of a regression line was mainly dependent on the ratio of the variability of the two measures. However, it was Carl Pearson in 1896, through the use of the product moment, discovered the parameters of regression slope and the correlation coefficient, establishing modern notation of linear regression.
To understand linear regression, one must understand regression. Regression analysis is a statistical technique for investigating and modeling the relationships between variables. Linear regression is the most used regression model and is the foundation for almost all other regression models. The linear regression model is stated as such: y equals beta sub 0 plus beta sub 1 multiplied by x plus epsilon, where x is called the predictor or regressor variable, y is the response variable, beta sub 0 is the intercept, beta sub 1 is the slope, and epsilon is the error. An important part of regression analysis is that the parameters, usually beta sub 0 and beta sub 1, are unknown and thus must be estimated. There are various ways to estimate these parameters. However, we will use and discuss the most common, the method of least squares estimation.
The ordinary least square estimators method uses parameter estimates to minimize a quantity called the residual sum of squares. Residual sum of squares, the sum of the squares of the residual, measures the difference between the data and the model's estimation. The least square estimators are found by setting the partial derivatives of the residual sum of squares with respect to beta 0 hat and beta 1 hat to 0, which produces equations that, when simplified, give the least square estimator. The least square estimator beta 0 hat is the intercept, which is equal to y bar minus beta 1 hat x bar. The least square estimator beta 1 hat, which is equal to the slope, is equal to the sum of the cross products over the sum of the squares of x, which is simplified to that mathematical notation. These numbers are then plugged into the following equation that forms the trend line: y hat is equal to beta 0 hat plus beta 1 hat x.
Linear regression has a wide range of uses. As one of the primary tools of data analysis, it can be found in any field with quantifiable data. With a set of data, we can establish linear equations using regression. For example, we can take a very large data set for velocity and time, say 1 million points of commercial flight data, and develop an equation that models flight velocity over time. Another use of linear regression is parameter estimation, which fits an equation to some data. For example, a measured force that is then applied to different masses and then accelerates. A regression plot of this gives a line that indicates the force and mass, with slope being equivalent to acceleration. The main use of regression is for the prediction of the response variable. This is often used to understand interactions between the variables, typically in a scientific or business pursuit. An example of this is predicting the time of the next eruption of Old Faithful based on the length of the most recent eruption. In this case, the length of the most recent eruption is the predictor variable, and the time until the next eruption is the response variable.
This is a mathematical expression of multiple linear regression. Y is a response variable and a dependent variable. X are predictors, independent variables, and regressors. Beta 0 is an intercept. Beta 1 to beta k are all estimated coefficients. They are parameters of the model function. The basic idea of multiple regression analysis is that although there is no determinate functional relationship between the independent variable and dependent variables, it is possible to find a mathematical expression that best represents the relationship between them. First, we need to select the data set and define a mathematical model. And then we summarize the model by using R. It is considered as the parameter estimations. We use RStudio to make the scatter plots. We will do the detection of outliers by using residuals versus fitted value plot, QQ plot, scale location plot, and leverage plot. Then we summarize the model function by RStudio. After that, we should do the significant tests, t-test, f-test, residual analysis, adjusted R-squared value, and finally, we should determine the estimation regression function for model prediction. We used RStudio as a tool to solve linear regression problems. We are going to use example professor reading, which from the textbook Applied Linear Regression Force Addition. Those are the 5 variables. We set 2 models. Model 1 is a simple linear regression example which have 1 predictor, and Model 2 is a multiple example which have 2 predictors. We should load a package which contains the data we need, then find the data, and attach to the data. Now we move to simple linear regression example. First, we set a Model 1. We used par method to divide the plot screen into 6 parts and making the scatter plot with a trending line, and we plot a function LM mode 1. We move to the plot screen. The first one, it is a scatter plot for quality versus clarity with a trending line, and they have a positive relationship. The second one is residuals versus fitted value graph. The outliers are pointed out in the graph. 76 is far away point. The third one is QQ graph, which is a probability graph. It shows the outliers. 76 is also far away. The fourth one is scale location graph. It is similar to residuals versus fitted value graph. It also shows outliers. 76 is still far away from the graph. The fifth one is leverage graph, which has Cook's distance line. For those points who are away of the Cook's distance line or approaching to Cook's distance line, they should be considered as outliers. 76 approaches to Cook's line. Overall, in order to make the result more accurate, we should delete the data row 76 from the datasets, and we go back to the summary, the mode 1 function. We see probability value are less than 0.05. Those 2 parameters are significant. P-value is really small. It shows that parameters are significant. Adjusted R-squared value is approach to 1. It means those 2 parameters have strong correlation. Then we get an estimated function. Then we move to multiple linear regression example. We set mode 2 and make the plots. We move to the plot screen. First graph shows the clarity and quality has the positive correlation. Second one shows the reader interest and quality also has the positive correlation. The following graphs shows the outliers. 76 is a faraway point. Overall, in order to make the result more accurate, we should delete the data row 76 from the datasets. And we go back to summary the mode 2 function. We can see probability values are all less than 0.05, which means the 3 coefficients are significant. Adjusted R-squared value is approach to 1. The range for the residuals is not big. It shows the correlation is very strong. P-value is very small. It is very significant. Then we get an estimated function for multiple linear regression.
The hazards of linear regression. Extrapolation is a hazard for linear regression because it is intended only for interpolation, or in other words, to model the range inside the measured parameters of the predictor. Thus, inaccurate modes may be taken outside of the measured parameters. Another hazard of linear regression is the bias towards the extrema of the x values. This is due to the slope of the least square depending heavily on the extrema value, while every other data point has an equal effect on the height of the line. We can see this effect in these graphs. After adding two data points, A and B, to the original graph, the regression line is changed. In fact, adding just one of these points to the original dataset changes the regression line substantially.
The hazard of outliers is very similar to the hazard of extrema. Just like extrema, outliers in the middle of the data can cause an error in the model of the regression. However, it is possible that there is an explanation for the occurrence of the outlier, which might be important. This is why many statistical methods have been made to determine whether an outlier is beneficial or should be rejected for the health of the model. Furthermore, the hazard of conditional regression is that predicting the predictor for a regression model of the response variable means that the accuracy of the model of the response variable is dependent on the accuracy of the prediction of the predictor variable. In layman's terms, if your initial evaluation of the variable is incorrect, then all your information is incorrect. Finally, I am sure you all have heard the phrase, correlation does not mean causation. This phrase is really important for linear regression. It is very easy for two unrelated variables in the real world to have a strong relationship, correlation, through regression. Additionally, it is quite possible for the response variable to be dependent on many different predictor variables, and thus the results of the regression could be skewed. So any information found about the cause and effect relationship should be tamed.
Ultimately, linear regression is one of the most useful tools in analyzing statistics if used properly, and will only become more ingrained in statistics as our digital world becomes an everyday feature in the analysis of our lives. Thank you for watching.